Thank you, Mike, for the great introduction in WACCM, and now I will go more into the details of chemistry and aerosols. I'm, by the way, now the Chemistry Climate Working Group co-chair, and we do have a new liaison for CAM-chem, which is Rebecca Buchholz. Our other co-chair is Rafa Fernandez, and our software engineer is Francis Whip. And so going to the next slide. Yeah, okay, so what I want to start with is some motivation on chemistry and aerosols, the importance of chemistry and aerosols for climate. And this is a figure from the recent IPCC report, ERA 5 Working Group 1 technical report. And what you see is the increase in effective radiative forcing since the 19th centuries. And what you see is really that greenhouse gases are the main driver of global warming, but there is also a lot of other gases that are very important, which are chemistry like ozone, nitrous oxides, halogenated gases that play a very important role in the warming of our planet as well. And in addition, of course, the tropospheric aerosols actually do show something like a negative forcing with the large uncertainty. So they counter the current warming of the greenhouse gases. And so it is very important if we want to understand climate change, if we want to understand what the future will bring for us, that we simulate aerosols in the climate system and describe them well in the models. So both chemistry and aerosols are important. And here's a little different view. This is the difference of the radiative forcing between pre-industrial and present day. And again, what you see is the main greenhouse gases have a very strong forcing, but really looking at the precursors of ozone, which is ozone effects are represented here in green. You do see that there is quite a bit of importance in ozone, but in addition, the precursors of aerosols, for instance, here sulfates and the aerosols themselves, organic carbons and black carbon, for example, have an important role in the radiative forcing, and especially not only through the direct effect of aerosols, but also the indirect effect, how they impact clouds. So again, importance here of prescribing aerosol and precursor aerosols is important, and as well as the interactions between the models, the cloud aerosol interactions. So what I want to do is also motivate not only the importance of chemistry for climate, but also for air quality. We do know that ozone pollution events happen, especially in cities, but also outside, and they are caused by the precursors that are emitted through traffic, industry, private use, farmland, and ozone, when produced and is in high values at the surface, is bad for human and ecosystems. It does damage tissues of the respiratory tract and cause inflammation, and has impacts also on plants. And in addition, particle matter is very important to be considered for pollution. And what we look at is often the PM2.5 and PM10 particle diameters that are less than 2.5 and 10 micrometers. And those are produced also by the aerosol precursors as well as by aerosols from our anthropogenic emissions, but also coming from now increasing fires with climate change and dust storms that are worsening. All of that impacts people as well as ecosystems. And we do have a bunch, so a high percentage and 7 million premature deaths due to pollution each year about. So how do we simulate aerosol in chemistry, which is really important? And Mike has talked about mostly the WACCM model, the high top model. And this is more an illustration for something like the chem height, the low top model reaching up to 40 kilometers, but it applies the same for the whole WACCM model, of course. So what you see is there is complication, the complicated coupling of the land model and the atmosphere. We do have all these emissions that come from the land, they emit precursors of ozone as well as aerosols, and then they cause pollution in the cities at the surface, but also they get transported up into the upper stratosphere, into the upper troposphere, sorry, and in part even into the stratosphere. They will be transported, they will be transformed chemically, as well as forming aerosols, and often reach even to remote regions like the Arctic and Antarctica and have influences there as well. So we need to describe, and we describe all of that in our model. And going to the next slide, this is somehow how we can describe it. The solution for each chemical species in our model. This is the change of the chemical species with the time step in the model, which is the production basically minus the loss, which is consistent of several terms. And so each of these components at each time step change the concentration with the sum of these changes as listed here. And those include like the emissions, as I said, then the gas phase chemistry, the aerosol processes, which include gas aerosol exchange, as well as heterogeneous reactions, the advection and diffusion of the transport, as I explained, and then the cloud aerosol processes that also include wet removal of aerosols, and the dry deposition and wet deposition of gases. And also those components with shorter lifetimes may experience differences if we change the time steps, but also if we change the order of operations in the results. So this has been all taken care of when you change something in the chemistry. So going now to somewhat like the life cycle in the model, the different processes that we describe here as an illustration. I talked about the emissions that are the different emissions that we consider in the model, and the chemistry, which are listed here, the radiation and transport, cloud processes, and eventually the removal. And so I want to go now in the following through the different processes and how they are more in detail described in the model and how you change them. I mean, I'm not talking about how you change them at the moment. You'll learn more about that in the tutorial on Friday. But so for surface emissions and concentrations, we divide this into two parts. One is the emissions that are emitted at the surface. This is the anthropogenic, biogenic emissions, biomass burning, ocean and soil, everything that comes from the surface. But then we also have the vertical emissions, and we call them in the model the external forcings. These are things like aircraft emission that get emitted in a certain altitude, the volcanoes that Mike talked about, power plants as well, that do not emit right at the surface, but at somewhat higher level. And then we have the second part, which is the surface concentrations, and we call those the lower boundary conditions, which is basically concentrations we fix at the surface, like greenhouse gases and other long-lived gases. I'm giving now two examples. This is an example for surface emissions, for example, NOx. And what you can see is really that these emissions are prescribed and they are changing. Here we have, for instance, in 1850, 1900, 1950, and 2000, you see that how the emissions are changing. More and more anthropogenic effects are visible, for instance, from pollution as well as from the shipping sector. And the other thing that I talked about was the lower boundary condition, or the concentrations that we basically constrain the model to certain fixed greenhouse gases like CO2, methane, because then the reason is it's important, for instance, for CMIP6 or other model comparisons, that we do prescribe concentrations. So we are sure that we they have the right, basically, or the same concentrations in the atmosphere. However, in our chemistry mechanism, in CAM-chem and WACCM, these chemicals, ozone, CO2 and methane, do still evolve and are chemically active. They're just prescribed at the surface. And here you see an example of, for instance, a future scenario, the RCP 6.0. So going to the next is the chemical mechanism. And The chemical mechanism, Mike has already talked a little bit about it for WACCM. This is an example or an illustration of the troposphere chemistry. It is quite complicated. You have various precursors that are entering the troposphere here for ozone, and then depending on conditions, ozone will form, ozone will also react with other chemistry. We do have reactions with sunlight, basically the photochemistry. We have the gas phase chemistry, heterogeneous chemistry, reactions in clouds, in particular SO2 forming sulfates, and so that's the aqueous phase chemistry. And then the formation of aerosols, for instance, secondary organic aerosols. And all these chemical mechanisms are available. And the most complicated one is the one in WACCM, which is what Mike already has explained, the troposphere, stratosphere, mesosphere, and lower thermosphere mechanism, or TSMLT. And this has the most species as well as the most reactions. But then if we go to CAM-chem, and as I said, CAM-chem is basically the low top model that reaches up to 40 kilometers, but it does still prescribe the stratosphere quite well. So we'll still include all the tropospheric and stratospheric solutions here. We do have a bunch of less of the photolysis reaction. This is because there's much more going on, as Mike explained, in regard to that in the mesosphere and lower thermosphere. And so then we already talked about the middle atmosphere version, and Mike didn't mention the MAD, the middle atmosphere plus D region ion chemistry, and he can tell you about that more if you have questions. But then there is the specified chemistry of WACCM, and basically chem, which is a specified chemistry, CAM-chem, or the just standard chem. And as you can see, this has way fewer species. This has way fewer reactions. And you may wonder, how is it then possible? How can you describe all this complicated chemistry in chem and use it? So here's one slide on that. So WACCM and CAM-chem have really the same atmospheric physics and resolution. There is differences in the chemistry. And what we usually do is we run WACCM or CAM-chem with a complicated chemistry, and then we will just use those information and prescribe these fields in chem. So they are not interactive, but often this is sufficient to really look at long climate simulations. So many things in chem are prescribed that are interactive in CAM-chem and WACCM with the full chemistry as listed here. I don't know if I admit this person, I just do that. So next is the aerosol model and the cloud interactions. And so what we are using as a standard aerosol model in CESM2 is the Modal aerosol model, or called MAM. And this consists of modes, the icon mode, accumulation mode, and coarse mode, and as well as a primary carbon mode. And basically the aerosol distribution in the atmosphere can be described by these modes. So instead of having a complicated description of all the sizes of the aerosols, this is a fairly cheap way to be able to describe aerosols in a reasonable way. This includes, though, all the aerosol microphysics, in some part nucleation, but certainly coagulation and other processes and sedimentation that are needed to describe the life cycle of the aerosols. The aerosols are internally mixed in these modes, and they, as I said, represent the aerosols quite well in both in the troposphere and also in the stratosphere in both CAM-chem and WACCM. The primary carbon mode had been added, which is now the MAM4 mode, which is basically adding somewhat to the accumulation modes in order to be able to consider changes of black carbon with time, because it changes its hydroscopicity and ages and becomes more hydrophilic with time and gets rained out. So it changes in lifetime. But in general, also the modes that you're seeing here are actually from the MAM5 model. The MAM6 model has slightly different width of the modes, and probably new versions will go back to this original size. Now, we do have a nice and very comprehensive description of secondary organic aerosols in both WACCM and CAM-chem. If we run with the full chemistry, we do use this volatility bin set VBS description with 5 volatility bins. They are interactive with land emissions and are more physical than what's actually in just CAM. CAM has a very simple approach because we cannot use this very comprehensive approach without having the OH and oxidants be more interactive for each time step. And now one slide to the aerosol cloud interactions. This is actually a slide from Wang et al. 2020 from the James paper that describes processes in E3SM. But our model, the CAM-chem and CESM has now also all these processes included besides maybe one, I think the representation of marine organic aerosol, which is currently implemented, but this is really a comprehensive way. We do include a lot of processes. That is the activation, basically, of aerosols, meaning they're forming cloud condensation nuclei, then the movements of cloud, the convective processes and activation, ice formations. And as I already said, we do have the chemistry, aqueous phase chemistry in this, as well as suspension of clouds, and things like resuspension of raindrops, and eventually wet removal. So there, if you want to learn more about this, this is a good paper to read up on it. And finally, on talking about the dry and wet deposition of gases, and aerosols. So the dry deposition is the uptake of chemistry constituencies by plants and soils, and that depend on the land type, roughness of surface, and is based on a resistance approach, which is shown here. You do have some parallel and linear resistors that are coupled together to really describe these dry deposition velocities based on different components in the land, like the dynamic sublayer, the interface sublayer, vegetational sublayer, and so on, as you can see here, also considering the surfaces, the stomata, and also the dry and wet surfaces. So this is the formulation for the deposition flux, which does depend on each species that is deposited. And so it's usually described here as a concentration in 10 meters. And in addition, we have wet removal, and the wet removal of aerosols was described in the slide before on the aerosol cloud processes. This is just for chemical constituencies. We do remove them based on rain and ice, and they are obviously linked to precipitation and both large scale and convection. But it's a very simple first order approach, which really depends on the fraction of the grid box from which traces have been removed and the loss rate. And so in my last few minutes, I want to give some examples. I haven't shown much on the evaluation of CAM-chem, but I mean, I would say the model is really in good agreement, especially for ozone, when we compare to long-term climatologies and ozone sound observations. But of course, we always also look at more local phenomena. And here, for instance, what we are using as an application is the CAM-chem version, which includes the spectral elements core and regional refinement over CONUS. AECOM has worked on this quite a bit. And this version is also called the Musica version 0, the multi-scale infrastructure for chemistry and aerosols. That basically is shown here on the bottom. So you compare a 1 degree model simulation to this regional refined model simulation on the bottom. This is surface ozone. And what we can really see is the improvement of maximum of ozone in some regions, as well as some of the structure and the movement. Another application that I want to show you is to understand better the composition of aerosols and chemistry in the Asian monsoon We have right now an ongoing aircraft campaign, which is the ACLIP campaign. And just at this moment, basically, while in Korea, there's a team of scientists that perform measurements with some 2 aircraft, and I tried to run this movie. And what they are sampling is various trace gases in basically the shedding region of the Asian monsoon. So what you can see here is CO, carbon monoxide, in over here the Asian continent, and we do see the emissions of CO going all the way up to 15 kilometers or higher. And then in July, August, there's always the anticyclone forming here that traps the pollutants. And also occasionally there are shedding events that move these pollutants over to the region where it can be sampled right from South Korea. And so people are right now running these aircraft campaigns to understand the composition as well as the movements into the stratosphere. And so I want to acknowledge various people here that contributed to this movie. And finally, I do want to talk about user support. We do have the CAM-chem and Musica websites in addition to what you're learning here. This website for CAM-chem helps you to understand more about if you want to change chemistry. In particular, if you want to change gas phase chemistry, we have examples here. And we also talk about pre-processing and post-processing, diagnostic packages here. And also, we do have a website that is the Musica website that helps you if you're interested to produce a regional refined grid with chemistry. And I'm showing the same slide here, but I updated it compared to Mike. And we do have Rebecca Bruchholz as our liaison, and she indeed has a different phone number than Mike. And with that, I want to stop and see if you have any questions. Thank you.